All right, today we're taking a look at the Quiz 4 preview. Lots of stuff we've gone over, so we'll jump right in here. Okay, factoring. Factor each completely. We're always looking first, of course, to see if the golden rule takes effect, if there's anything in common that I could take out. If there is, great, I do it. If not, I'm going to start looking for some other clues. Like, for instance, here, I don't have a value in front of my x squared. I don't have an x squared coefficient. So I can treat this like a diamond problem. I need two numbers that multiply to get the number on the end, add to get the number in the middle. So I look at my clues. Multiply to get a positive means they're both positive or both negative. But since they add to a negative, I know both of my numeric values are going to be negative. And now it just becomes what multiplies to 24 and adds to 14. 6 and 4, no, 12 and 2. I get that set, and I go. Now, the second one can be really easy, or it could take some work. Depends on how I'm looking at things. One of the little clues I'm always looking for, besides the golden rule, if there's anything in common, is, do I see perfect squares? Because if I do, in this case, I have a perfect square trinomial. Perfect square trinomials, I ask myself, what do I square to get the first term? 3x. What do I square to get the last term? 5. And then I look at the sign in the middle, and that tells me how to get there. Now, for some of you watching this and going, now wait a minute, where did the minus 30 go? Remember, 3x minus 5 quantity squared means that in actuality, I have two of these. And if I go through and I FOIL it, outside, inside, last, there's my negative 30x. So it's still there, it's just in a compacted form. So something to keep in mind. Okay. Number 3. Ooh, the golden rule finally comes into play. What do these two terms have in common? They both have a 4. They both have an x. At this point, I'm trying to figure out, what's left over that I could work with. 4 times what gets me to 20? 5. X times what gets me to x squared? X. And 4x times what gets me to 4x? 1, and that's as far as I can go. Now, I always want to look and make sure I can't factor what's in the parentheses, but a lot of times that's not going to be the case. So I get up to 4. And I'm like, all right. Now, 4's got some issues going on here. And again, it's all going to depend on your route of tackling this. Some of you may be good enough feeling with guess and check that you can grab your pencil and go, all right, let's see here. Get my sets of parentheses. Now 6. 6 could be 6 and 1. It could be 3 and 2. Let's try 3 and 2 here first. And then 12. Well, let's see. 12, I'm thinking 6 and 4. So if I do 6 and 4, 12 and 12, yeah, that's not going to get me where I want to go. Let's see here. 6 and 4. Harty at 6 and 2. Oh, Harty, you're a silly, silly man. So let's see. 2 and 6. 4 and 18. Yeah, that's still not getting me where I want to go. And some of you are kind of bopping along here going, let's see, 3 and 4. 3 and 4. No. 4 and 3. Ooh, wait a minute. 8 and 9. Different signs, so I got one positive and one negative. But my negative product needs to be the bigger one. So, negative 9 plus 8 is negative 1, and I'm good. Now, if some of you don't like playing the guess and check like that, or maybe you want to do something that's a little more visual and put the different factors that are possible down so you can just sort of mentally do it this way, that's fine. But I'm going to show you one other way on number 6 that you can handle this if you don't like playing the guess and check game on a problem like that. Here, perfect squares, got to know them. Whatever I square to get my first term, whatever I square to get my second term. And again, since I'm looking for a negative product, plus minus with my difference of squares. So we're good there. Even though Harty just saw something that you may have caught, maybe you didn't catch. I always talk about the golden rule, and I look at this one and I go, hey, something divides out of there. I kind of noticed it when I looked at these because I'm like, wait a minute, I could still take a 3 out of those. So what's the biggest number that divides into both of those? Well, 9 does. So let's see if that changes things. Oh, and it does. Because now I can square 2x to get 4x squared. I can square 3 to get 9. Okay. So you're like, okay, Harty, how would you grade that? If I did this on a quiz, what would happen? On a 2-point question, I'd probably ding you for a half out of 2. So it's not a huge error, but not looking at the golden rule first and getting that common factor out is something we got to make sure that we do. So we want to get down to this answer down here. All right. So then, as promised, we get to number 6. Now again, some of you with the guess and check will be able to knock this out because I don't have any choices for my first term. It's 5x and x. I know they're all pluses, so I'm good there. So 18, I'm thinking, okay, 9 and 2, 9 and 2, that'd be 19, nope. Let's see, 9 and 2, 6 and 3. Let's try 6 and 3. 6 and 3, ooh, 6 and 3, 15 and 6 is 21. Okay, what if that's not your strength? You're like, I am visual, I don't like just doing all this mental math. Okay, here's your backup plan, here's your option. We chatted about it a little bit when we were doing our factoring lesson before. If your strength doesn't lie in this area, slide and divide can be your friend. So again, I take that 5, I'd multiply it, I'd slide it down to the end. Now, then I still have some work ahead of me because I need to find 2 numbers that multiply to 90 but still will add up to 21. Now, maybe you're like, I don't know. Worst case scenario, I write down every combo I can think of. Maybe those are the only 2 I can think of, I don't know. And then I would go to the calculator and I'd start with small numbers and I'd start dividing them into 90 until I find 2 that add up to 21. And that can take some time sometimes. Oh, finally. So I'd go ahead, write those down, but I'm not done. This wouldn't foil out to that. Don't forget the divide part. That would slide back to the front. 15 divided by 5 is 3. Happy camper. Okay, that's the type of thing that we're working on. Okay, so either one of those ways works. This one takes a little longer, but I know I'm going to get to the right answer right away. This one, I play a little more guess and check. It's up to you. So moving on. Okay, we're going to write in radical form. Don't simplify. Remember, this is always exponent over root. So if I'm writing it as a radical, the 1 is my exponent, the 4 is my little number outside the root. I'm done. It's true on any of these. My exponent, my root. It tells me not to simplify, so I'm not going to. And then it works exactly the opposite way in exponent form. Exponent root, 3 over 5. Okay, exponent root, 7 over 4. And that's all I'm doing. So don't make life more complicated than it needs to be. When we get to 11 through 13, we're using our rules. When we're multiplying with exponents, we add them together. But of course, I have to have a common denominator to add them together. My common denominator in this case would be 6. So what do I multiply 3 by to get to 6? 2. So I do the same thing to the numerator to get 4 over 6. 5 over 6 is already all good. I add those up. And again, simplify all the way. Can I reduce the fraction at this point? Yeah, I can divide both of those by 3 and get to the answer. But again, use your brains on this. Don't just go to the calculator and take the easy way out, because sometimes that's going to bite you in the butt. Okay, 12. Exponent rules tell me this time I'm going to subtract the exponents. Again, I need to have a common denominator, which in this case would be 12, unless you went the other way and just multiplied them, it'd be 24, but I'd have to reduce it. So I look and I'm like, okay, 4 times what gets me to 12? 3. Get that set. 6 times what gets me to 12? 2. Multiply my numerator like that. I'm good there. But you've got to work with these rules. If you haven't been doing the homework, it's kind of hard to remember all these rules. And then finally, simplifying, does 5 evenly go into 15? Or you could look at it and say, hey, can I do the exponent over root thing? I can, as long as I remember to simplify it. And I'm good there. So as we get down towards 14, write the expression in simplest form, no decimals. Repeat that again, no. So remember my little root number out here, like, oh, these are the ones we got to break down, aren't they? Yup. Largest perfect square that's a factor of 32, which would be 16. And we talked about how we can do this a couple of different ways. I can either break it into 2 separate radicals, one that breaks down, is perfect and gets out of radical jail, and one that isn't, or I can just do them as I go. So I'm going to do one each way. This one I'll actually break down the first one. So I got a 16, I got a 2. Okay. 2 does go evenly into 4, so that all goes in our perfect one. Ooh, 2 doesn't totally go into 5 though. So remember, we got to break that up into 2 pieces that add up to 5. So 4 would be the biggest multiple that goes in. Leave me 1 left over. 4 and 1 is 5. And then z, I run into the same issue. 2 doesn't evenly go into 7. Break it up. 6 and 1. So I'm not done yet. So here's what I have to do. This is our perfect radical. They are all going to get out of radical jail because they have changed their ways. So we got 4x squared, because again, how many times does this go in? Y squared z to the 3rd. And then the square root of 2yz. That is simplified. So if you need to break it into pieces, do. Otherwise, I can look and go, okay, oh, cubed root this time, it's a 3. Cubed root of 27 is 3, okay. 3 evenly goes into 18 6 times. Blasted, couldn't just be perfect all the way through. 3 into 10, remember, we're going to bust that up into 9 and 1. 3 goes into 9 3 times. I got 1 left over. I go on with my life. 16. The squared's just going to distribute through. 5 squared, it's not under a radical. Ooh, but the square root of 6, square root and squared are inverses or opposites. They cancel. I get my answer. And if one of them looks hard, again, this is why I was mentioning before, really needing to know your cubes and squares. You're like, okay, cubes. Let's see. 1, 8. No. You're like, dang, Harty. Cube. Oh, 8? Is 8 really the biggest one that goes in there? It is this time. So the cubed root of 8 is 2. 45 still stuck here in radical jail, acting irrationally. Okay, 3 doesn't go into 4 evenly, so this again breaks down into x to the 3rd and x. So 3 goes into 3 once. Got 1 left over to put in there. Then my y's, same thing. 3 doesn't evenly go into 7. So I can do 6 and 1. 3 goes into 6 twice. 1 left over. Again, break it into 2 and do it. Do it as you go. Both get me to the same spot. Happy camper either way. All right, next part. And I got to be a little cautious here. Even though it says step function, I still need to make sure I don't do an absolute value function. So again, step functions, the ones that look like steps. The ones that we graph with dots like a regular line. So if I was graphing the line negative 2x, I'd have a y-intercept at 0. Then I'd go down 2 and right 1, down 2 and right 1. And I'm going to keep doing that until I run out of room here. Okay. And I can even go the other way a little bit. But then don't stop, because now it'd just be the line y equals 2x. This is a step function. So we're going to create those little steps. Open circles on the right. Boy, these are little. So they look like little tiny steps all the way down. So it looks like a real wide version of that line. So that's one of the things I need to do. And I do the same thing on 19. If I was graphing this line, x plus 3. Okay. Slope is 1. Get those going. And again, it's always to the right, open circle. To the right, open circle. Okay. Not just plain lines and absolute value. The brackets tell me that it's going to be a step function. So again, nothing too bad. Graph the following functions. Okay. Here you have choices. But here's one thing you do not have a choice about. Start your line here. Now, that does not mean I ignore y-intercepts. So like if I'm doing this first one, and I go and I'm using a pencil, which is smart on these. Down 1, over 1, down. Okay, so I make a bunch of points as though I'm graphing the line. But then I go back and I say, okay, we're starting at 1. It's less than that. So I'm looking at points like 1 and 0 and negative 1. So I go, okay, here's x is 1, here's my dot. It's a closed dot because it's or equal to. And then starting to the left of that, I'm going to connect the dots. I don't need these other ones. Or if you even wanted to, you could just plug those 3 numbers in here and just plot those 3 points and do it. It's absolutely an acceptable way to do it. Same thing here. Okay, I'm going to start at 1, but I'm going to graph my line first. 1, 2, 3, 1, 2, 1, 2, 3. Now this one's a little more interesting. You're like, okay, start at 1. Harty, there's not a dot there. Well, if I were to draw the line through, where does it look like it'd be? Well, almost the exact same point, just about. So I'm going to have an open circle there to the best of my ability. And here, since the values are greater, it tells me I'm going to go to the right. Connect the dots, and I'm done. But notice, both lines start at x equals 1, but it doesn't mean the intercept moves with it. Like I start here and I go up 2 and then start. That's not what it means. Graph the line, then go back and look at the restriction for what part of the line that you want. We need to chat some more about that. We can. All right, so solve by showing all work. Graph the solution, state the solution in interval notation. Okay, couple things here. This is an and statement. It's less than. And statement typically means we're going to have endpoints. We're going to be shading in the middle. So when I go to make my 2 expressions, well, what was that again? 2 expressions. Flip my arrow, change my sign. what I'm going to do. So once we do have those two separated, I'm going to go ahead and solve them like I normally would. Be careful though. What happens when I have to divide both sides by a negative in order to isolate my x term? Gotta flip the arrow, otherwise I'm going to get exactly the wrong part of the graph. And we'll talk a little bit about how you can make sure that you don't screw that up in just a second. We'll go ahead and get our other one solved for as well. Now again, this is one of those times, 13/3 is the more proper way to do it, but if you go ahead here and call it 4 1/3 or 4.33, I'm not going to yell on the screen. So here's why it's so important to know in advance, if it's an and or statement, to have an idea of what this should look like. Because now, when I go to graph this, so x is greater than or equal to -1, x is less than or equal to 4 1/3, I'm real confident that I did this correctly because I'm getting the graph that I was looking for. If I'd have forgotten to flip these arrows and I'd have had it going this way and this way, I'd have looked at it and said, wait a minute, something's wrong, and maybe it would have clicked in my head how that works. So you start to see how knowing all these little hints and things is something that's really, really helpful when you're doing it. So then my interval notation just goes from left to right. And I've got to remember to get that in there. Same thing going on 22. Ooh, another little place with a caveat here. Before I can split it into two, I have to isolate the absolute value. Now I can go ahead and get it split into two. Again, and or greater than is or. So I kind of know what this should look like. Here I flip my arrow, switch my sign, a couple of quick one-steppers. Again, you can do your number line how you like. Just make sure you have equal values. You know, that you're counting by equals. I'm counting by fives here. I can't just put one line with -3, one with 7, and call it a day. Greater than 7. Less than -3. Looking good, looking good. And again, my interval notation from left to right. Left is forever left to -infinity till I get to -3. Start up again at 7. And head off to the right. Okay, so lots of little things here with signs and then arrow flip and isolating. You've really got to be cautious when you're doing those to make sure this is going well for you. And finally, write the equation that represents the graphed absolute value function. So remember, to know this, I need two things. I need my vertex, and I need my slope. I need my a value. So my vertex, that's pretty easy to find, -3, 3. So I got my h and my k here. And then my slope, again, let's go to the nearest one here. 1, 2, 1, 2. And some of you may again be thinking back for a minute and go, well, wait a minute. Up 2 and over 2, you know, you went left 2. Why isn't it -2? Why isn't it a -1 slope? Remember, when we're talking about air quote slope with an absolute value, we're talking about does it open up positive or down negative. That's the only thing we're thinking about with these. So when I go to do this, remember my expression is y equals a x minus h, or x then the opposite of h, plus k. And we're set. So this is just some quick overviews of all the sections that we did throughout this part. Well, we only got a couple parts left before the unit test, so if you're having some issues, watch some parts over. If there's a certain part you're looking, find that note sheet, maybe rewatch that video or just do a couple extra problems or ask me about it. But do look this stuff over because it's going to come quick.